Now students, we have already discussed how magnetic field is produced about a conductor. That is, when a conductor is taken such that I amount of current is flowing through it, we can easily find the amount of magnetic field and the direction of magnetic field across it. How? By using right hand thumb rule, right? That means magnetic lines of force are emerging from this region and entering at this region. So we have represented the emerging points with dots and the entering points with cross, right? This is simple. Now there is another phenomena that always happens when a current carrying conductor with, instead of conductor, I will be more frequently using the word wire because you guys are more familiar with the term wire. So when a current carrying conductor is placed in a magnetic field, it experiences a force. So how? Suppose this is a uniform magnetic field. Now why do physicists always use the terms like uniform magnetic field instead of magnetic field? See, physics is a very detailed subject. You have to be very cautious about the words which you are using. Uniform magnetic fields means magnetic field has equal strength at all the points. And if we just say the magnetic field, it could be uniform or non-uniform. So based on that difference, there would be a different force acting on the conductor, right? So that is why we sometimes we have to be very careful about what we say. Now consider this uniform magnetic field in this region. How is this magnetic field represented? All the magnetic lines of force are entering this conductor, that is this plane, right? They are entering, going inwards. Now I have placed a current carrying conductor like this. The current is flowing in this direction. So the phenomena is this current carrying conductor is going to experience a force which will be acting on it, and this force is depending on it. This force depends on the magnetic field, that is strength of magnetic field present in this region, and is also proportional to amount of current flowing in this conductor, right? So I am not going to give you the full value of the formula because the formula is not in your syllabus yet. You will be studying it in +2. Now otherwise the formula is BIL, magnetic field, current and length of the conductor placed. But anyhow, the force experienced in this wire or the conductor when it is placed in a magnetic field is given by a very simple rule. We are talking about only the direction, not the magnitude, and the direction is given by Fleming's left hand rule. So the rule is Fleming's left hand rule. So in some textbooks they have not mentioned the word Fleming's, they have only mentioned the word left hand rule. So the rule states like this: if you place thumb, first finger and middle finger of your left hand in 3 mutually perpendicular directions, this is how they are in 3 mutually perpendicular directions. So I'll repeat it again: when we place thumb, first finger and middle finger in 3 mutually perpendicular directions such that this is representing force, this is representing field, this is representing current. So I'll rephrase it: such that first finger is representing the direction of magnetic field and middle finger is representing the direction of flow of current, then the thumb will represent the force experienced by the conductor. So thumb is giving you the direction of force which is being experienced by the conductor. So we have thumb, we have first finger and we have middle finger, right? So we have to place these 3 fingers in mutually perpendicular directions such that first finger is in the direction of magnetic field and middle finger is in the direction of flow of current. So when you place these two, you will automatically get the direction of force experienced, which will be given by thumb, force experienced. Okay, so let's see it in this example. What is the direction of magnetic field here? Vertically inwards. So which is magnetic field? First finger, right? And then I have to use my left hand, right? So this is how I place the first finger. Then this middle finger is to represent the direction of flow of current. So I'll be rotating my hand like this. So this will give you a better view. So first I did this and then this, right? So this is the direction of flow of current. So thumb is giving me the direction of force, that is this conductor is going to experience a force in upward direction. So if this would have been my conductor, it would have moved up. Simple. So this is the phenomena of force experienced by a current carrying conductor or force experienced by a conductor when it is placed in a magnetic field. Now we very well use the same phenomena and make it work for our benefit in terms of electric motor. How? To understand that concept, what we are going to do, we are going to implicate this force thing on two wires, okay, such that the flow of current in both the wires is in different direction. So instead of force, what we have done is we have introduced torque. How? Suppose this is the direction of magnetic field, okay. Now instead of one current carrying conductor, I have placed a loop. Now the direction of flow of current in the loop is, let us say, this direction, okay. So how is this going to rotate? Let me take something rectangular. I don't have anything. So yeah, this is how you'll have to understand. Let's apply force field current. First of all, in this loop, in this wire, field is in this direction, current, the middle finger, it has to go up. So that means the force is being directed in the inward of this plane. Same ways, in this case, force field current, field is in this direction, current is in vertically downward direction, that means force is outwards. So what is happening to these two wires? This is experience a force inside and this is experience a force outwards. So this whole loop is going to rotate. What is happening? It is rotating because this loop is right now under the action of two equal and anti-parallel forces. So these forces would create a torque, okay. So they'll start rotating. This is the phenomena. So how we have changed the sentence? There is a force which is being experienced by a current carrying conductor if it is placed in a magnetic field. True. But if instead of current carrying conductor I have a current carrying coil, then force would be replaced by torque. So when a current carrying coil is placed in a magnetic field, it experiences a torque, okay. The same phenomena is used for our benefit, what we do in electric motor. So what is the direction, what is the circuit diagram for motor? Consider these are magnets, north and south pole magnets, okay, and this is our loop. Now this loop was rotating like this, okay, simple. In this loop, this part is connected with carbon brushes like this. These are carbon brushes. I'll explain you why we use carbon brushes. And this is ring, half semicircular ring, okay. Similarly, this wire as well, I have to make it a bit more shorter. So yeah, this wire is also connected with, let me bold the ring part. These are called split rings, okay. I'll come back to this topic again. These are again carbon brushes and this is my ring. Now what is the reason for the ring? I'll tell you. The connections are made from here, the cells or the source which is providing the current to flow in this wire or the loop. I make an arrow above it because I am showing it that this cell circuit or the cells, this circuit or the source of EMF, this is inculcated with a variable resistor which is called rheostat. So all I want to say is that this is a variable voltage. I can change the value of voltage anytime. That is why I made an arrow out of it. And then the switch. This is the simplest diagram for, no, it will go like where? Like this. So this is a simple diagram for electric motor. Now what is happening? See, the source is offering current. The current is flowing through this. Now through this ring, current will flow in the conductor and the conductor will start rotating. But once one loop is completed, this wire comes in contact with this ring and this wire goes in contact with that ring, right? And that is why the current will still flow in the same direction and the coil is going to experience the torque in the same direction, and that is why it will keep on revolving. So this is the block diagram of AC or DC. This is a DC generator because we have applied a DC current. So DC motor. Okay, so let's start it from the beginning. We started with the fact that current carrying coil, current carrying conductor placed in a magnetic field experiences a force. We changed it. current carrying coil placed in a magnetic field experiences a torque, and this is the working principle behind DC motor. So what would be the principle? You have to explain three terms in any such sort of questions. So number one is principle, number two is construction, and number three is working. Okay, so number one principle is it works on the principle that current carrying coil placed in a magnetic field experiences a torque. Number two, construction. It consists of, you have to summarize all the devices or all the apparatus used here in the circuit one by one, and you have to give their working in just one short line. That is, in construction, number one, field magnets. They are used to provide magnetic field. Number two, coil. They are often referred to as armature coil because it consists of n number of turns, because one singular loop is not going to give us that much torque. Because what we are going to do with this, what we want from this is, I want it to rotate because that is the job of motor. But what do we do out of it? We connect this motor part with anything which you want to rotate. Suppose this is a fan, so it will rotate the fan, right? That is the point. So more number of loops means more amount of torque, that means more rotation or solid rotation. Now second is armature coil to provide rotation to the coil. Third is this is called commutator arrangement. Commutator, commutator arrangement. This commutator arrangement provides a constant connection from battery to the loop. How? As soon as this wire finishes off with half of the ring, it goes in contact with the another wire. The purpose of this carbon brushes was that, suppose this is my wire, okay, and this is my ring, this one, my hand. So the wire is rotating in connection with the ring, but at any point, due to any technical snag, it can get minorly out of contact, right? Because these are very stiff arrangements. So if it gets out of connection, the whole circuit breaks and there will be not any flow of current and it will stop rotating. So to prevent that thing from happening, between this wire and this circular ring, we apply soft carbon brushes which are very flexible. So they are now connected with the wire, and these carbon brushes are always in contact with this ring. That is the purpose of attaching these wires with the carbon brushes, and then carbon brushes are made to rotate with the, or making the constant connection with the rings. Then we have rings and then the source. This is how you write construction. And then working, you have to explain working by starting with the point that consider this loop is A, B, C, D, which is connected to source via or through commutator arrangement. Now, according to direction of flow of current in A to B or in AB, which is from A to B, by applying Fleming's left hand rule, we see that the force experienced by this wire is in vertically outward direction, whereas force experienced by the wire CD is in vertically downward direction or inverse direction. So hence this loop is under the action of two equal and anti-parallel forces, due to which they constitute a couple, and the moment of force is given by, what is moment of force? Given by torque. So this torque makes this rotation possible. Now go back to the lower part of the diagram. Now these wires are in constant contact with the source because of carbon brushes and slip rings. There are two types. One is split rings. These are split rings. Another one is slip rings. Slip rings will be using in generator. So the wires are in constant connection with the rings through, or with the split rings using carbon brushes, and this process goes on, and we are able to rotate it very easily. Now what do we make out of it? What do we do with this? The part of armature coil which is rotating is connected to whatever which we have to rotate. For example, grinder blades, fans, anything which rotates, that is, or DC motor simply. So this is the basic DC motor. Alright.